doing this as a slideshow, and I won't be able to do annotations on the screen. But as you can see, my notes are pretty much handwritten. So hopefully that should be good enough for this lecture. So I hope you have already seen some kind of quantum teleportation with diagrams. And in this lecture, we are going to revisit quantum teleportation, but in much more detail. So first of all, can everyone see my mouse pointer, the black mouse pointer? So I cannot see the chat right now, so you'll have to unmute yourself and speak.
Yes, Hamza, we can see it.
Okay, perfect.
Yes,
So first,
yes, we can.
perfect. So first, let me remind you about the cup state and the cap test. So the cup state we represent like this, and you know that we read all the diagrams from bottom to top. And I hope you have seen the traditional mathematical representation of the cup state. And the dual of the cup state is something called a cap test or a cap effect. And you must also have seen that, if you have a diagram that is composed of boxes and wires, you can slide boxes along wires, and you can also slide boxes along cups and caps. And you must also have seen that if you have a wire that looks like a snake, then you can also like yank the wire and get the straight wire. So, and as I've stated, in the diagrams, time flows from bottom to top. If you have two boxes connected like this, the diamond box is applied first, and the heart box is applied later. So time flows from bottom to top, whereas space is from left to right. So if you have two boxes like these, this means that you have two operations that are being applied at the same time. Since I cannot see your faces, please interrupt me if you have any question. Okay, so let's quickly revisit quantum teleportation from the previous lectures. So using this box sliding rule, we can have a trivial description of quantum teleportation. So say you have two parties, Andrea and Blaise, and these two parties can be far, far away. So say Alice is, let's say, at the North Pole and Blaise is at the South Pole. And for teleportation for the teleportation protocol, what is essential is a cup state. So this is the cup state. A cup state is essentially an entangled state. And so if Andrea applies this operation at her side, this is operationally equivalent to Blaise applying this operation at the other side. Notice that we have got this equation by using the sliding rule. So let's say Andrea and Blaise are at two very different locations, and Andrea wants to send a quantum state to Blaise. What does Andrea do? First, like I said, they need to have Andrea and Blaise need to share an entangled state, which is this cup. And so this is this diamond box. This diamond state is the state that Andrea needs to teleport to Blaise. So Andrea needs to, in the teleportation protocol, Andrea needs to apply an operation that acts on both this diamond state and the part of the bell state that Andrea has. And essentially, you can see if teleportation works, then we should, after applying some diagrammatic rewrite rules, we should get the right-hand side. So what is this operation? What is this question mark? This operation is the cap test. And using the sliding rule, you can see that this state is teleported to Blaise. So this is all recap. You must have seen it already. Now, in quantum theory, you know that when you apply tests, which means that when you perform measurements, then the outcomes are not deterministic. The outcomes are probabilistic. So for the quantum teleportation protocol to work, you may need to apply some error correction. So in the example that you have seen already, we don't have any error. So we know that this cap effect is a deterministic effect, and we know that this this entangled state is also, you can prepare it deterministically. Of course, here I'm not talking about the experimental errors that you can have or noise that you can have when you're doing it experimentally. Here I'm not talking about that. I'm just talking about the bare bones process. But even then, you can have some kind of indeterminism in the cap test. So the cap test is essentially a measurement in the Bell basis. Now, if you have studied quantum information or quantum computing, you would know that uh, a Bell basis measurement has 4 states in its basis. So there can be 4 possible outcomes of the measurement, and these outcomes can be represented diagrammatically like this. So here these different boxes are basically unitary operations, and applying these unitary operations to the cap test, you can get you can represent some kind of error. So let's say Andrea applies this Bell basis measurement. So if the outcome of the measurement is this one, which is the vanilla cap test, then Blaze doesn't need to apply any correction, because this box can be slid to the other side and teleportation happens, right? But if there is an error, so say the outcome of the measurement is this one, then if you slide these boxes along the wire, you get this error at the other side. So this is not perfect quantum teleportation. Now, to remove this error, Blaze needs to apply some error correction. Now, since this is a unitary operator, the error correction must be its inverse. So the error correction, the inverse of this unitary operator is represented like this. Note that this is the same box, but flipped vertically. Now these corrections, this correction cancels out with the error, which basically means that if you apply the inverse of the unitary to the unitary, then you get an identity, and we get perfect quantum teleportation. Now you can do. Now, what about the other cases? You can have similar kind of diagrammatic representations for the other cases. So this is the one with the smiley error. This is the one with the fourth kind of error. So essentially, teleportation is achieved by a bit of sliding and a bit of yanking, and but the question is, sure, if we know what the error is, then we can apply error correction. But how does, remember, Andrea and Blaze are at 2 different locations. So how would Blaze know which error correction to apply, given that Andrea is at a distance far, far away? So to apply the right error correction, Blaze and Andrea needs to communicate the error, the outcome of the Bell basis measurement to Blaze, and this is achieved through classical communication. Right. So again, in this diagram, Andrea wants to teleport this this diagram state to Blaze. A certain error, applying the Bell basis measurement, a certain outcome is achieved. Andrea looks at that outcome and then encodes that outcome into a classical channel, and that classical channel is connected to Blaze. Now, looking at that information from the classical channel, Blaze can apply the error correction. Since there are there are four possibilities. Four possibilities. Andrea needs to send 2 bits because, as you know, 1 bit encodes uh, uh, 2 possibilities, and if you have 2 bits, then you can have 4 possibilities. So in this sense, teleportation is not instantaneous because uh, the information about the error is transmitted through a classical channel, and classical channel, as you all know, the speed of information transmission through classical channel is limited by the speed of light. We cannot send the classical information faster than the speed of light. So the question is, if teleportation is not instantaneous, why do we bother so much about teleportation? What's so interesting about it? The answer is that using just 2 bits of classical information, we can transmit potentially infinite amount of information, because the quantum state can be any state uh, from the Bloch sphere, right? So without so when the quantum state is teleported from Andrea to Blaise, even Andrea doesn't know what the quantum state is. If she has not created the quantum state, she doesn't know which quantum state it is. So without determining the quantum state, we can uh, send that quantum state from one location to another in a very secure way using just 2 bits of classical information. And again, I must emphasize that this quantum state can be any state from the Bloch. Sorry, is there a question? Sorry, I cannot hear you properly. Can you repeat if there's a question?
That is the question.
Is there a question? By the way, if there are any questions in the chat, so unfortunately I cannot see the chat. If there are any questions in the chat, may I ask the host to let me know? Or if anyone wants to ask any question, you are very free. Please feel free to unmute and interrupt me. Okay. Yeah, is there a question? Should we go ahead? Is everything clear?
Yeah, you can go ahead.
Okay, thank you. So essentially, we can send a quantum state by just making a phone call, and I mean by phone call, I'm saying metaphorically, right? I mean, you just need you just need a classical channel with a capacity of 2 bits of information. That's all you need to do. And of course, you also need to have an entangled state, which is a cup state that is shared between Andrea and Blaise. So that is essential to do quantum teleportation. Okay. I hope you have also seen spiders in the previous lectures. Please, can you confirm you have seen spiders?
Yes, please.
Perfect. Right. So spiders are very general kinds of diagrams that you can use to represent quantum states, quantum effects, unitaries. So essentially, spiders let us describe the structure that is inside these boxes. So these boxes are at a certain level of abstraction. If you want to look deeper into these processes, then you need spiders. And to represent all of quantum theory, you need 2 kinds of spiders. You need red spider, green spider. In some textbooks or in some research papers, sometimes they use white and gray spiders, but they're essentially the same thing. So a white spider is the green spider, and the gray spider is the red spider. So these 2 colors actually represent 2 bases. So the green spider represents the Z basis, if I'm not forgetting, and the red spider represents the X basis. So diagrams that are made of these red and green spiders are called ZX diagrams, and this diagrammatic representation is called the ZX calculus. So here are some examples of states and effects made of red and green spiders, and here are some examples of gates. This is a so this is a Pauli Z gate. This is a C0 gate. So in the C0 gate, the qubit at the left side is the control qubit, and the qubit at the right side is the target qubit. And you must have seen some rules that characterize how these spiders interact. So if you have two red spiders, they fuse and the phases are added. So 180 is 360, that's 0. And again, this is just for recalling yanking of spiders. So green spiders can also be fused. Okay, so before we look at quantum teleportation in terms of spiders, let's do a short digression and look at quantum test computing or measurement-based quantum computing. So in measurement-based quantum computing, quantum computations are performed by doing measurement. This is different from circuit-based quantum computing. In circuit-based quantum computing, you have quantum states, you apply some unitary operations, and then you perform measurement at the end. In quantum test computing or measurement-based quantum computing, you apply measurements in a particular order, and the order of the measurements determine the calculation that is performed or the computation that is performed. So here is one example. I'm going to show you one example of measurement-based quantum computing. Say we have a state, this heart-shaped state. It's a qubit, and say we want to move this qubit from this wire to this wire. The question is what kind of operation or what kind of measurement we can perform. So we can do this by applying a C0 gate. So if we insert a C0 gate in this box, we get this diagram. And now you can apply some spider fusion. We can fuse these two red spiders. Okay. So as you can see in this diagram, this question mark box has one output. So if we apply a C0 gate, we have to take care of this out. We have to get rid of the other output as well. And this can be done by applying this green spider here, which is a test. So now we can apply spider fusion. So we can fuse these two red spiders. We can fuse these two green spiders. We get this diagram. And you must have seen another rule which says that if you have a spider with two legs and zero phase, then that's essentially a wire. So this is a wire and this is a wire. We get this diagram, and again, we can slide this box. So we have achieved the original task of moving this quantum state or qubit from this wire to this wire. So this is one example of quantum test computing or measurement-based quantum computing. It is quantum test computing because here a test is performed as part of the computation, or a test or a measurement is performed. It's the same thing. Now, sorry, is there a question?
Yes, please.
Yes, please.
Please, how will you, like from what you just did, I would like to know how you know if you are supposed to use the C0 gate, and also if other gates could be used in this scenario.
Yeah, you can use some other kind of operation. You can definitely use that, but I think this is one simple example. So I mean, for example, you can use we could also have used, for example, so between these two green spiders, we could have used two Hadamard gates, for example. They would cancel out, right? But I mean, that's a very trivial example of another operation that you can do. So yeah, I mean, I hope that answers your question. So this is just one of the simple ways to do it, but essentially you can do some other kind of operation that does that.
Thank you, sir.
Yeah, is there another question?
No, sir.
Okay, thank you. Okay, but then again, so the main task, the main problem in measurement-based quantum computing is to correct errors. So as I said before, when we apply measurements in quantum physics, the outcomes are not deterministic. The outcomes of measurement are not deterministic. There are usually multiple possibilities, right? So if we want to apply this test, we usually perform a measurement which can give two kinds of outcomes, right? So to give you a very simple example, if you make a measurement in the z basis, right, then you can have a state that is, you can have a 0 state or a 1 state as the outcome, right? I mean, think of a Stern-Gerlach experiment. You can have two kinds of outcomes, but you cannot predict which outcome you are going to get. You can only calculate the probability of the outcome, right? In the case of a z basis or an x basis measurement, the probabilities are 50-50. So the problem is, if you don't get the desired outcome, what do? You apply error correction. So, for example, in the previous example, we wanted to apply this measurement, but this measurement doesn't come for free. It is part of a measurement which can be this measurement 50% of the time and this measurement 50% of the time. So say the outcome is this test with 180-degree phase. Now this is an error, and you can see that this error propagates. So after applying spider fusion and simplifying further by replacing this with an identity, the red spider has no phase, so it is essentially a wire. You can see that in the final diagram we have this error. And what do? So this error is again a unitary. We can apply its inverse to counteract its effect. So how do we fix the error? We apply this 180 degrees spider, the green spider here. Now you can see that after spider fusions, after simplifying the diagram, we get these two spiders together, and these two spiders cancel out. So we get the desired outcome. If you would like to keep the error there, then obviously we don't apply error correction. So in a very general setting, we can have a diagram like this. So say you can have an error which is represented by this random phase represented by a spade symbol, and okay, so here I'm representing this spade as an arbitrary measurement. So say I wanted to apply a measurement.
Hello, Hamza. Hello.
Hello. Yeah. Go ahead.
Yeah, please can you go back to the.
Sorry. I can.
The other slide before this one.
Is there a question? Okay. So this is a general measurement. So this is a green spider with an arbitrary phase represented by a spade, and ideally we would like, I mean, after simplification we get a state which is modified by this unitary. But this measurement also doesn't come for free. We could have an error, which we can represent by this spade added with 180 degrees phase. Now, again, if we want to remove this error, we need to apply the inverse of the 180 degree phase rotation, which is again a 180 degree phase rotation. So this we would apply here, and then after simplification, we would get the desired state. Now, again, notice that the measurement is applied on the first qubit, whereas the correction is applied on the second qubit. So again, this is a very simple example, but in more complicated examples of measurement-based quantum computing, you usually have a number of measurements and a number of corrections, and they have to be applied in a certain order. So for example, if we had 3 qubits, then we would do 2 measurements and 2 corrections. And those measurements have to be in a certain order for the right computation to work. So again, because this is not the main topic of this lecture, I'm going to leave it here, and then we can go back to quantum teleportation. So again, we have an entangled state, a cup state shared between Andrea and Blaise, and we have another wire. And so this is the wire that Andrea has, and this is essentially the state that is to be teleported is connected to this wire. So here, the state to be teleported is the diamond state. Again, so now we are going to do teleportation using spiders, using ZX diagrams. So notice that we can represent the cap test as this diagram. So the right-hand side can be represented as this diagram. You know that the green spider and red spider with 0 phase and 2 wires are essentially just wires. So we can replace the right-hand diagram with this diagram, and using spider fusion, we can get the diagram at the left-hand side. Now again, these the red and green spiders at the top, they are measurements, right? And you know that measurements are not deterministic, so there can be some kind of error there. I mean, here we can also call them maybe boxes because they are not certain. Again, so now we have 2 measurements. If we had 1 measurement, then we could get 2 possible outcomes. If we have 2 measurements, we can have 4 possible outcomes. So these 4 outcomes are represented by these diagrams. So test 1 is when you have no error. Test 2 is when you have an error in the red spider. Test 3 is when you have an error in the green spider. And if you have errors in both spiders, these errors are basically phases. Then you have test 4. So in the diagram that we saw previously, we applied a cap test, and there was a possibility of an error, and that error was propagated to the other side. Now, we can replace this cap test with the error with one of these 4 tests that we have drawn. So it's up to us. I mean, these boxes with the different symbols, they are, I mean, you can choose any symbols to represent these boxes. So we wouldn't worry too much about what these, about matching these with the errors. But of course, if there's no error, then that's a plain old cap test. If there's an error, then there has to be some phase, right? So instead of this cap test with this box, I'm using one of the tests with the errors. Now, after this is just part of the teleportation diagram. I'm not showing you the state that is to be teleported. Now, if I apply spider fusion, what do I get? These two green spiders fuse, the red spiders fuse. The red spider becomes the identity, so it's just a wire. And the green spider can be, we can slide the green spider to the other side. So remember, the wire at the bottom is the wire is to be connected to the state that is to be teleported. So if we have an error in the measurement, that means that the state is teleported, but it is also modified by this unitary, which is the error. So there has to be some error correction, and that error correction has to be by Blaze. So here are the four cases. If you have no error, we get this wire, we get just a plain wire. If you have an error in the red spider, then you have 180 degrees phase in the red spider. Likewise for the green, if you have errors in both spiders, then you get this situation. Now this is the full protocol. So Andrea Blaze, Andrea wants to apply a measurement in the Bell basis. By the way, this, if you are curious about what this is setting of the measurement basis. So again, this is just a C0 gate basically. And to apply a measure, to perform a measurement in the Bell basis, you have to use a C0 gate. And again, after a C0 gate, if you make measurements in green spider and red spider, that is essentially the Bell basis measurement. Okay, so again, if there is no error, then there are no phases. You get just the plain old wire that looks like a snake. You can yank the wire, and you get the diagram with the right-hand side, which basically shows that the quantum information is transmitted from Andrea to Blaze. If there is an error, that error has to be communicated, and we can represent this communication through this squiggly wire. And again, the rest is simple. You do spider fusion, you apply the identity rule, you slide the error at the other side, and because the correction has been applied, these two spiders cancel out by fusion, and you get the identity wire. Now, again, you can identify the other cases as well. As long as the errors are applied correctly and in the right order, you get teleportation. Okay, so we have seen quantum teleportation, its representation, and how to do calculations in the protocol using diagrams. Just to remind you that for Blaze to apply the right correction, 2 bits of classical information has to be transmitted from Andrea, which again, you don't have to represent it like this, but if you want to be very explicit, then you can do it using these squiggly wires. To show you some more examples of states that can be, I mean, you can teleport any quantum state from Andrea to Blaze. Here are some examples. You can have some green spiders, red spiders with some phases. You can have some more complicated kind of states that you want to send. So I would like to conclude here by saying that the real magic of quantum teleportation is that there are infinitely many possible states that can be transmitted using just 2 bits of classical information, and an entangled state that is shared between the 2 parties. Now, if you have any questions, please let me know. If you have any general questions about, this whole way to do quantum theory, about quantum pictorialism, about this formalism, I'm also happy to answer those kind of questions, like more general questions than what we discussed in this lecture. Any questions at all? So initially, my plan was to join this meeting with my iPad, and I was planning to also show you the traditional Hilbert space representation of these diagrams as well. Unfortunately, I'm unable to join using my iPad. I don't know why. But if you are curious about any of that, I'm happy to send you my lecture notes that I used to prepare this lecture. All right, I guess we don't have any questions, so we can conclude here.
Okay. I think there's a question in the chat.
Okay. Yeah.
So it's saying, can the spider be used in Shell's algorithm and also the Bell state?
Yeah. The spiders can be used in the Shor's algorithm and the Bell state. I don't have the Shor's algorithm with me right now, but let me quickly tell you how to represent the Bell state. So look at this cap test. So this cap test is the dual of the Bell state, right? So you can represent the Bell state using spiders by just vertically flipping this diagram. That's the Bell state. And yes, you can do essentially any quantum computing protocol that you can do using traditional methods. You can do it using spiders. So there's a completeness result which says that the ZX calculus is complete for finite dimensional Hilbert spaces and transformations between them, which means that any quantum computing protocol, any quantum theory calculation that you can do using Hilbert spaces, finite dimensional Hilbert spaces, you can do that using spiders. So I would encourage you to try some quantum computing protocols. First of all, represent those protocols and then try to do the calculations using diagrams. And sometimes the calculations become quite intuitive when you are doing it using diagrams. That's a very good question, by the way. Okay, yeah. So one of you says that they would like to have the lecture notes. So I'll share this slide deck with you as well as the lecture notes. So I'll send it to the organizers and then hopefully we can share it with you. Any other questions before we conclude?
Okay, I think there's another question asking for the use cases of spider.
Okay, can you elaborate what do you mean by use cases of spider?
Okay, can you elaborate? Then type.
Okay, use case. So I don't know what you mean by use cases, but let me just show you some, I don't know, some examples from a paper. So this is a paper that is freely available online. This is called ZX Calculus for the Working Computer Scientist. It's a very nice expository article on the ZX Calculus, and you don't need to have any kind of background in ZX Calculus to be able to read this paper. It's very introductory, but it also gives some examples of what you can do using these diagrams. So let me first quickly show you an example. So this is a typical quantum circuit that you must have seen in quantum computing textbooks. We have 3 states. We have a Hadamard gate. We have a couple of C0 gates. Now, usually what we do is we have a circuit diagram and we have the traditional matrix representations of these qubits and these logic gates, right? And if you want to simplify this circuit, what you do is you perform the simplification using matrices, matrix multiplication, tensor multiplication, stuff like that. And then you draw the final circuit, the simplified circuit. But using spiders, you can do it all diagrammatically. So first you need to map this to the spider diagram, which is what you have on the right hand side. So these are basically the red spiders that you have seen. These white spiders are the green spiders, and this is the Hadamard gate. And the Hadamard gate itself is made of 3 spiders, which they haven't shown here. Now, using the diagrammatic rules, you can simplify this diagram like this. So as you can see, there is spider fusion, and then there is the identity rule, there is color change rule. If you haven't seen these rules, you will see these rules in the later lectures. And at the end, we have this state, which is the GHC state. So this is one example of how these spiders are used. If you want to know how these spiders are related to the traditional notation, let me show you some examples. So this is a white spider, which corresponds to the green spider that we have seen, and this is how it is interpreted in the traditional notation. The phase of the spider is here, alpha, and these are so this is in terms of kits and bras. Likewise, for the red spider, we have this interpretation. Just to give you some more examples, this is a Z spider rotation with the alpha phase. This is what it looks like in the bracket notation, and this is in the matrix notation. Likewise for the red spider. So again, there's a lot more in this paper, and I'll just give you a quick glimpse of the table of contents. So if you see this paper, you can see some examples of measurement-based quantum computing, some other quantum computing protocols. You can also see the quantum teleportation stuff here, and there are many more rules as well. And I hope there are some examples of some quantum computing algorithms like Shor's algorithm in this, somewhere around this, or maybe the Deutsch algorithm. But yeah, I would highly recommend this paper. It's called ZX Calculus for the Working Computer Scientist. It is available on arXiv. Yeah, you can get a link of this paper. Let me share it here. All right, I hope I've answered your questions, but yeah, this was fun. I'll share my notes and my lecture slides with you. Thanks for joining.
Okay. Thank you very much, Hamza, for this presentation. And thank you to the participants for joining today's sessions. A few announcements. We'll be having a session tomorrow, as we have a class tomorrow, at the same time. So I'll see you then. Thank you again, Hamza, for the meeting.
No worries.
Have a nice day.
Yeah. Thank you. Bye.